So yes, tomorrow is advising day, so if you haven't gotten a note from your advisor about meeting with them, you should probably try contacting them personally. Say, can I set up a meeting with you sometime tomorrow? That is expected that you try to meet with your advisor at some time tomorrow. If you can, I mean, you could try another day, but tomorrow is supposed to be the ideal day for that. All right, here's our lecture today, lecture number 16. Lecture A, we're going to focus on hypothesis testing, also called significance testing. In fact, the title of this section in our book is Tests of Significance. For population mean, when the population standard deviation is known, again, that's an unrealistic assumption. Usually, if you don't know the population mean, you're not going to know the population standard deviation. But to keep things as simple as possible, because they are already hard enough as it is, we go ahead and assume the population standard deviation is known here in chapter 6. In the next chapter, we get rid of that assumption and we have to estimate the population standard deviation as well. And it does modify what we have to do with it. Lecture B, I'm sure I'll have more to say about hypothesis testing, and then I want to get into simulating more with Rod Carewer's baseball statistics, binomial random variables, do something different than I did last time. This is going to be a harder one than what we did last time, but I think it is worthwhile to do. I did get the Adrian Peterson simulations working, so I'll show you what I got with that too, and talk about how it might be useful. I think probably in the next class period, I'll talk about simulating a Poisson, and then probably after that we'll talk about simulating normal random variables, in addition to other stuff that we're doing. Okay, so I would call this lecture A today, and maybe the beginning of lecture B, probably the most important thing for the whole semester here, to really, really pay attention, okay? Smile. It's hard, but it's good. This is the crux of the course right here, okay? Lots of ideas and terminology. It's going to be challenging, but pay attention, you'll be okay. On the quiz, by the way, there will be more with card probability, so I will once again show you this on the quiz. But for the moment, we're coming up back to hypothesis testing. Oh, I did want to go over the learning strategies. I think we better save that maybe for lecture B, though. So let's keep going. All right, here was our example from last time, our introduction to hypothesis testing. Let's consider the same situation again. Hypothesis testing, also known as tests of significance. Modified an example in the book. Okay? Survey of study habits and attitudes, this psychological test that measures people's attitudes towards school and studying. And there's a teacher who suspects that adult students over the age of 30 have a higher mean score than the entire U.S. population of all students. The claim is, for all students, the mean is 115 and the standard deviation is 30, but this teacher suspects that her adult students have better attitudes, so she gives the sample, this test, to 36 adult students who are 30 years old or older. Here are the questions we thought of last time. How should we set up the test of the teacher's hypothesis? I won't write as much as I did last lecture on the board. Let me just summarize what I wrote. We had a null hypothesis, an alternative hypothesis. H sub 0, or H naught for short, represents the null hypothesis. The 0 there sometimes is described as a naught, H naught. H sub A, also sometimes in other books called H sub 1, represents the alternative hypothesis. We put an A there to remind ourselves that it's the alternative hypothesis. These hypotheses are assumptions, hypotheses, theories about values of population parameters. That's the first important thing to realize. These are not about statistics. These are about population parameters. In this case, a population mean, mu. The alternative hypothesis, HA, is quite often what the person who's doing the test, it's what their theory is. Okay, and by the way, mu here, since her theory is about adult students, age 30 years or older, this mu, this population mean, is supposed to represent the mean score for these adult students, for all adult students, not just your sample, for all adult students in the whole country age 30 years and older. She thinks their mean score will be bigger than 115, bigger than the claimed mean score for all students, evidently traditional college age 18 to 22 and older. She thinks the adult students have a higher mean score. That's her hypothesis, that's her theory, that she's going to test against a null hypothesis, the opposite of this. Technically speaking, the null hypothesis is the opposite of this one, meaning mu is less than or equal to 115. However, for simplicity's sake, for the sake of keeping the calculations conceptually as simple as possible, you go ahead and assume the null hypothesis is the boundary value, mu is 115, exactly. But in reality, in the background, the null hypothesis really includes values of mu that are less than 115 as well, like 114 or 113, or some decimal. These are means, so they don't have to equal whole numbers. Got that? I wrote down last time a two-step process. You should make sure when you are writing down hypotheses that you not only write what I have here, that's the second step, but you also write the first step where I said define the parameter you're trying to test. Look back at the last lecture, lecture 15b, I think. I wrote down what mu equaled. I made a mistake at first. I said it was just mu was the mean for all students, but no, she's testing the adult students. So the mu here is the mean score for all adult students age 30 and older. That should be written down. It's a good thing to write it down, okay? To be clear about what you're testing. It also reminds you you're testing about parameters. I should never ever see statistics here. I should never see x bars here when I'm writing down the hypotheses. When I first taught this class, I assumed that was pretty obvious, but I learned in seeing students' tests that it wasn't obvious. So now I'm emphasizing it. Write down population parameters here, never statistics. Everything I'm saying is really key here. You want to try to catch everything I'm saying, write down subtle details. We also asked this question: if she found the mean score for her random sample to be higher than 15, if she found an x bar for her sample to be higher than 115, what would that mean about her hypothesis? Is her alternative hypothesis true if x bar is 116 or 117 or 118? Does that mean she's right? It's kind of a trick question, and kind of not. The answer is, you still don't know for sure if she's right or wrong. It's still not absolutely clear if she gets a sample mean bigger than 115, whether the alternative hypothesis is true or not. It still might be true, it might not be true. However, there's an idea about strength of evidence against the null and in favor of her alternative. The bigger x bar is, the stronger the evidence against the null hypothesis and therefore in favor of her alternative hypothesis. Therefore, what I'm trying to say is, if she gets an x bar of 130 or 140 or 150, that's definitely stronger evidence against the truth of this null hypothesis and in favor of her alternative hypothesis than getting an x bar of just like 116 or 117. Get the basic idea of that? Values of the sample mean, x bar, a statistic, further away from the null value of mu is stronger evidence against the null hypothesis and in favor of her alternative hypothesis. Therefore, she'd be more likely to say, yes, I'm right. I have real strong evidence against the null if x bar is further away from 115 than if it's real close to 115. Of course, if it's less than 115, then she has no evidence that she's right, essentially. I mean, she still could be right, but she doesn't have very strong evidence against the null if x bar was less than 115. So it's a matter of strength of evidence. Strong evidence is called statistically significant evidence.
calculations. What if her mean score was 120? What if it was 130? How do you assess the strength of the evidence against the null hypothesis? It's a probability calculation. Suppose she observes an x bar value of 120 to start with. The question is that a likely value of x bar if the null is true? So I'm about to do a probability calculation, assuming the null is true. It's really a conditional probability calculation, and I will emphasize that at first, but then after I emphasize that, then I will ignore the vertical line with conditional probability. What's the probability, P, of getting an x bar of 120 or bigger, say, if the null is true, if mu is 115? You see how I'm writing that as a conditional probability here with this vertical line? This notation is important. You've got to get the idea of the notation. This whole thing, this whole crazy thing represents one number, a probability. It's the probability of observing in a simple random sample of the given size 36 in this case, a sample mean of 120 or greater if you assume, if it is given that the null is true, if mu is really 115. It's not going to be a zero probability. It could happen by chance. How do you calculate the probability? You use the central limit theorem. I should really write an approximately equal to here. Again, in this class, there's so many approximately equals to everywhere that that's something I'm not super picky about you writing. Just want to write an equal sign. In reality, pretty much everything's an approximation in this class. I'm going to standardize x bar. Remember this by the central limit theorem, which could be on today's quiz. By the central limit theorem is approximately normal with a mean equal to the mean of the population and a standard deviation equal to the standard deviation of the population divided by the square root of the sample size. Sample size 36 here. So for this example, what's the mean of the population? That's the 115. You're trusting this claim about all college students. You're trusting that it's right. 115. Well, actually, I guess I'm assuming it's right because in my probability calculation, that's just the assumption I'm making. I'm actually assuming it's right about mu itself for the adult students. And I'm going to go ahead and assume the standard deviation of 30 for all college students reflects the standard deviation for the adult students as well. And the sample size is 36. Square root of 36 is 6. 30 divided by 6 is 5. So my sampling distribution for x bar is approximately normal with a mean of 115 and a standard deviation of 5. So when converting to z now, you need to subtract 115 and divide by 5, not 30. (120 minus 115). I'm converting the 120 here now to the corresponding z-score. 120 minus 115 over 5, which is 5 over 5, which is 1. What's the probability that z is greater than or equal to 1? A standard normal. Should be able to do that in your head, actually. 68, 95, 99.7 rule. 68% are going to be within one standard deviation of the mean, leaving 32% for the two tails. 16% for the right tail by symmetry. It's about 16%. You can do those calculations in your head if you try hard enough. You can. I'm confident you can. More precisely, do 1 minus 0.8413. This probability is about 0.1587. You probably should round that to 16% though. What does this tell us? What's the moral of the story? Why did we do this calculation? What it tells us is the likelihood of observing a value of the sample statistic here as extreme as 120 or more extreme, thus the greater than or equal to, under the assumption that the null hypothesis is true. If that probability is really, really small, then we observe something really, really rare if the null is true, and so therefore we think the null is not true. We have strong evidence against it. I'll say that again. This is the key statistical logic, okay? If in this probability calculation we got the probability really, really small, maybe 1% or less, maybe 5% or less, it depends on your definition of really, really small. If we had gotten a real small probability, then we would have observed a rare event, a sample statistic equal to 120, when the null is true. Therefore, we think the null is false. We have strong evidence against it. Now, this probability that I got is kind of small, 16%, about 1 out of 6 or so chance. Kind of small, but not really, really small. It's some evidence against the null, but not real strong evidence against the null. And with traditional kinds of ways of thinking about this, this is not strong evidence against the null, not strong enough evidence, typically, to say I'm going to reject the null. I've got some evidence that the null is wrong and the alternative is true, but not statistically significant evidence by most measures. So therefore, what do we say? You could say, we think the null is true, you could say that. She probably would say, well, I just don't have strong enough evidence against it. I'm going to fail to reject, I'm going to accept the null. I don't maybe really want to, because I think I'm right, still. But honesty compels me to say, I don't have real strong evidence against the null, I'm not going to reject it. On the other hand, 130 is further away. More extreme. I'm going to get a bigger or smaller probability? Smaller. If x bar now is 130, redo the calculation, change the 120 to 130. Same assumption, still assume the null is true. This is a 130 here. 15 divided by 5 is 3. That probability is going to be very, very small. Less than a 1% chance. One minus 0.9987, about 0.0013, 0.13%. Very, very small. That's strong evidence against the null, and we would reject the null. This is statistically significant evidence against the null. This probability that I calculated for these two examples has got a special name. It's called a p-value. P-value for the test. Why is it called a p-value? Because it's a probability. They just couldn't think of anything else to call it. It's a probability. It's a common probability to calculate in statistics. And the early statisticians, therefore, decided to call it a p-value. For this test. There are p-values for lots of other tests, too. This is definitely not the only statistical test you can do. There's probably hundreds out there. This is just the simplest kind. Here's another example. Spending on housing. This is going to be similar to a couple homework problems that you are going to have for next time. I just changed the numbers a bit and changed the city from Cleveland to Minneapolis. We are very Minnesota-centric in this class. Proud to be. Okay. The Census Bureau reports that households in the U.S. spend an average of 33% of total spending on housing. Actually, that was changed from the book. The book claimed it was 31%. I don't know if it's right or not. Probably neither of those is right. And let's pretend the standard deviation is 9.2%. Again, that was a changed number from the book's exercise. A realtor thinks they spend less than that in Minneapolis. Based on a simple random sample of 50 households in Minneapolis, the realtor finds that they spend 30.8% of their spending on housing, less than 33%. But is it statistically significant less? That's maybe not the best way to say it. Is the realtor right? Quick answer to that question is, you don't know for sure. Might be right, might be wrong. Is it strong evidence that the realtor's right, or weak evidence that the realtor's right? The p-value calculation answers that. Is the possible answer with the given information? Well, yes, sort of. We can do a p-value calculation and assess the strength of the evidence about whether the realtor's right or not. What are the hypotheses? First step, define your parameter that you're testing. I want you to do this, okay? Even if the book doesn't say to do it, and they typically don't, I want you to do this. Let mu, this is the parameter I'm testing, equal what? It's going to be a mean, a population mean. What population mean? The realtor's testing households in Minneapolis. So this has got to be the mean percent of spending on housing for households in Minneapolis. Because that's what's being tested. Let mu equal the mean percentage of income, or total spending, I guess I should say. Total spending on housing for households in Minneapolis. Yes, it's kind of a pain to have to write all that out, but it's so worth it. For clarity, in communicating to the reader, for clarity and understanding things yourself, do this every time. Even if the book doesn't ask you to do it. As your first step, define the parameter you are testing. We're testing households in Minneapolis. So mu is a mean percentage of spending for households in Minneapolis. Now write down your hypotheses. What is the realtor's theory? You're pretending you're the realtor. The realtor's theory is that households in Minneapolis spend less. Therefore, the alternative is that mu is less than 33%. And the null, technically speaking, then would be that mu is greater than or equal to 33%. The opposite of the alternative. However, again, for simplicity's sake, we go ahead and assume it takes on the boundary value for the null hypothesis. Mu equals 33%. That's the claimed percentage for all households in the entire country. We're not going to try to argue whether that's right or not. We're trusting that it's right. We are testing for households in Minneapolis. Is it a reflection of reality or not? And the theory here for the realtor is that it's mu is less than 33%. Okay? Now percentages are proportions, so you might be thinking of these as p-values, not in this sense, but as proportion values, population proportions. And we could think of it that way, but it's going to be fine. I'm mimicking the book here. We're going to be fine with just treating these as means, because they could be thought of as means as well. Mean percentages. Now to answer the questions, not, not for certain, but with strength of evidence, do the p-value calculation. Okay, and so I'm about to do here. What's the probability of observing an x bar sample mean value as extreme or more extreme as what was actually observed? 30.8% is what's actually observed if you assume the null is true. That's the assumption you make when you do the p-value calculation. You assume the null is true. You give it the benefit of the doubt. This test is a less than sign in the alternative hypothesis. The previous one was a greater than sign. You're really calculating an area to the right of something. For that one, that's called a right-tailed test. For this one, we're going to calculate the area to the left of something, a less than or equal to. It's going to be what's called a left-tailed test. It's going to be an area under a normal curve to the left of a certain number. This is called a left-tailed test. That's terminology you should know as well. As extreme or more extreme is always with respect to the direction of the alternative hypothesis. This is a less than sign to the left. Less than or equal to there. We're assuming the null is true, so technically speaking, this is a conditional probability. However, from this point on, I won't bother writing it as a conditional probability, but I should remember that in my mind. Now you convert to z. By the central limit theorem, x bar is approximately normal if your sample size is large enough, and I guess we're assuming 50 is large enough to make this a decent approximation. Convert the 30.8 to z. You can include the percent sign in there or not. It would cancel anyway in the z-score calculation. Maybe I should include it. It's going to cancel out because the sigma is going to have a percent sign as well, so the percent sign goes away. The sigma is 9.2%. Don't stop there. What am I forgetting? I'm not actually forgetting it. What am I pretending I'm forgetting? Divide by the square root of n. Don't forget that. That's the most common mistake. And divide by it. Don't multiply it. That's another common mistake, is people multiply for some reason. No, divide by it. N is 50. Okay, I'm going to need my calculator for this one. .8 minus 33, that's negative 2.2. But let's figure out the bottom first. 9.2 divided by square root of 50. Well, about 1.3. That's the standard deviation of the sampling distribution of x bar. Sigma over square root of n. Again, do the subtraction on top, you get negative 2.2. So we get negative 2.2 divided by that number we just figured out is negative 1.69. So we get a negative 1.69 here. It's going to be a fairly small probability. How small? Go to table A. Negative 1.69. The area to the left of it. So that gets 0.0455. I purposely made this example so that this comes out a little less than 5% because 5% is a common standard of smallness or very smallness. 5% or less. It's not that it's, rock solid, you can't argue with it as a standard of very smallness. It's just a commonly used one. So by commonly used standards, this being less than 0.05, less than 5%, this would commonly be thought of as statistically significant evidence against the null to say the null is false and the alternative is true. It's pretty strong evidence. It's not as strong as it could be if it were less than 1%. It's pretty strong evidence against the null, and most people typically say, if they have no other idea of what to pick for a standard of smallness or standard of very smallness, they commonly pick 5%. If the book doesn't tell you what to pick for your standard of smallness, you can pick 5% here initially, but I think later on we might want to use better judgment perhaps, based on the nature of the example and how bad it would be if you rejected the null when the null is true, or failed to reject the null when the null is false. We'll talk about this actually next time in depth. But for the moment, if the book doesn't tell you what to use as a standard of very small p-value, you can choose 5% if you want. Just make a note to the grader about it, okay, that you decided to use 5%. So again, that's less than 5%, pretty small. We have pretty good evidence against the null, so we reject the null and we say the alternative is true. It seems like the realtor is right. We have strong evidence, pretty strong evidence that the realtor is right. Is the realtor right for sure? No. We just have pretty strong evidence that the realtor is right. So it's possible to answer, sort of, is the answer to the last question. Yes, we can say we've got strong evidence against the null, we think the realtor is right. But it's not a for sure thing. The realtor might still be wrong. You might be 33% or even higher for Minneapolis, even based on a sample mean of 30.8%. I'm going to take the quiz in 1 minute. Let me just mention, as a preview of what we're going to do after the quiz, that we can put a twist on this example and say, well, what if the realtor doesn't have a theory of what the answer is? In the previous slide, the realtor thought the answer was less than 33%. But what if the realtor has no idea how much households spend on housing in Minneapolis? What do you do then? Should you still do a hypothesis test? The answer is, well, you can, but you do have to modify when you do it. We'll talk about that after the quiz. So put things away.